In this equation, we're going to look at a basic introduction to the origins of the ideal gas equation. So the thought behind this video is to give you a real sense of the link between the kinetic energy of the gas molecules and pressure, what pressure is inherently. And this is a standard presentation that you'll find in any textbook. So if you consider a room in which a gas can move, so if you consider a room in which a gas can move, and we allow the gas molecule to bounce off a wall and then recoil, then this gas molecule has to obey certain conservation laws. Let's say it hits a wall. So I'm going to call this a wall of area A. So that gas molecule has hit the wall of area A, but the gas molecule must conserve linear momentum. The gas molecule must conserve linear momentum. And we just mean good old Newtonian momentum, nothing fancier. So momentum here, let's just call it the product of mass and velocity. So let the gas molecule have a mass, let it have a velocity, and so its product, mass times velocity, is the momentum. Get a little bit more light in the room, there you go. Okay. So if we know we've conserved linear momentum, the linear momentum is actually along the red lines. So just in the x-axis, so let this be the x-axis. So we're only considering one dimension, just the x-axis, so you can move in the positive x-axis, the negative x-axis. Okay, so the momentum in the x-axis, the velocity in the x-axis. Okay, so we'll just ground ourselves in that axis for now. And we know that linear momentum is conserved. So I'm interested in the change. There must be a change overall in momentum because, well, I have to be careful. Linear momentum is conserved, so what do I mean by change? I mean a change in direction. There we go. Change in direction because it's velocity, not speed. So the change or the reorientation of our linear momentum in the x-axis is going to be 2 lots of mvx. So essentially, imagine the gas molecule is moving in the positive x direction. Then abruptly, this vector is going to go to 0. So it's changed by 1 factor of mvx because vx suddenly became 0. But then, because of conservation of linear momentum, it has to come back again and with the same vector. So essentially, the magnitude of the red vector below is the same as the top one. That's what I mean by conservation of linear momentum. But clearly it's in the opposite direction. So I lose a unit of mv positive x when I hit the wall, but I reclaim the same magnitude of mvx in the other direction. So I change by 2 multiples of mvx. Okay? That's only for one atom. So for n atoms, then the change in linear momentum in the x-axis is n to mvx. So I just multiply by n for n atoms in a volume V, I have the change in linear momentum is going to be n to mvx per unit volume. Well, this normalizes per unit volume, but then I can scale to any volume I like. So then I can just multiply this whole thing by a volume. So essentially I've added a dummy volume. Okay, I've taken the change in linear momentum for one gas, scaled it by n, normalized it per unit volume, and then scaled it to any volume I like. Now, why not just cancel these volumes? Well, there's a reason. I'm going to substitute one of them in for something else. So this volume I'm going to rewrite. I'm going to rewrite thusly. So volume is area times by distance. So let volume equal an area times by another length, another distance that we'll call length. Okay, so volume is area times by an extra dimension of length. And on this occasion, let length be velocity by the change in time. So this is a common equation that people have seen in grade school. Distance is speed times time. So now I've got volume is equal to area times by length, where length is v delta t. That's my volume here, and now I can put the rest in. So n over v twice mv x, and this is the change in linear momentum in the x-axis. So we have this equation here. It looks a little bit messy, but we have, and I should put the fact that I'm only looking at the x-axis here. Eventually we'll get rid of the label x and we'll scale up to 3 dimensions. Notice I have a Vx here and a Vx here. Let's pool those together. So let's pool those together. So I'll get rid of the Vx here and I'll rewrite it over here. And this is starting to look a little bit interesting. It's starting to look a little bit interesting because now I've got mass velocity squared. Well, that's almost looking like kinetic energy, which would be great, because I'm considering the motion of a gas molecule, and kinetic energy is the energy of motion. So I just have to manipulate it a little bit to make it look like real kinetic energy. But so far it's looking doable. Now you can see why I didn't want to cancel off my dummy index here, my volume. I am going to get rid of this factor of 2 though. Why would I get rid of this factor of 2 here? Well, I'm assuming that the gas molecule is moving in a predictable direction. But we know from kinetic molecular theory of gases that gases take the shape of their container. They're statistically equally likely to move in any which way, in any direction. So because they're equally likely to move in any direction, they're equally likely to move in the negative x and the positive x direction. So I need a denominator factor of 2 in here to represent the fact that only 50% of them will be moving towards this wall. So if I divide by 50%, it would cancel this coefficient 2 away here. Okay, so now I've incorporated the fact that only half of my population is going to be moving in that direction. The other half would be going in that direction. Why am I only considering 2 directions? Remember, I'm only considering the x-axis for now. The 50-50 would apply to the y and the z as well, but we're not looking at those yet. Why are we interested in linear momentum? Well, just a snapshot of where we're headed with this. I'm interested ultimately in pressure. But pressure, we know, is force per unit area. And force is change in momentum per unit time. So ultimately, the way I'm going to rig this is we're looking at linear momentum. We'll look at the frequency of change of linear momentum to get force. And then once we have force, we'll look at force per unit area, ultimately to get to pressure. So that's where we're going. Okay, so we've got our change in momentum here. Let's go ahead and divide it by delta t, ultimately, which is just going to get rid of this delta t here. So we just write the force, which right now is in the x-axis. The pen's misbehaving. Is going to be n over v. So n over v. And then I have mvx squared. A. I've gotten rid of the delta t because I divided by delta t to convert the momentum into force. A couple of things I want to do now. I want to get rid of the x label. So we're just going to scale up to 3 dimensions. You don't have to do it now. We can do it a bit later, but we'll do it now because it's on my radar to do it now. We know that v squared, total velocity squared, is velocity squared in the x direction and the velocity squared in the y direction and the velocity squared in the z direction, in the 3 Cartesian axes, x, y, and z. So far, the label I have Vx squared is only 33% of what I need, which is V squared. So I know that Vx squared is only a third of V squared. Why a third? Because it's one of 3. Okay. So I can substitute in Vx squared where I have Vx squared here. I can sub in V squared and I have the addition of a factor of a third to add. So this implies that F, I lose my X label now, is N, the total number of molecules over the volume, mv squared, I've lost my X label, area. So now I'm in 3 dimensions. And I have that factor of a third. So I lost the label and I inherited the factor of a third. Let's go ahead and convert force to pressure by dividing through by area. So pressure, the only difference is now we're going to lose that term A. So mv squared and that factor of a third. So I've got an equation for pressure. And now I'm really going to hone in on this mv squared over 2. This mv squared over 2, if I were to put, and I'll do it in red so it's clear, if I were to put a 2 in here, well, I can't just do that, can I? So I'd have to also put a 2 as a numerator as well. So I've just multiplied and divided by 2, which I'm allowed to do. I haven't done anything net. But now this thing in the parentheses is now kinetic energy. So recall the kinetic energy is mv squared over 2. Now, this is how you would derive kinetic energy, and I have a video on that you're welcome to look at. But we know that kinetic energy mv squared over 2 is also equal to 3 over 2 kT. So here we've got mass velocity squared over 2. Here we have mass velocity squared over 2, and here we have 3 over 2 kT. So rather than write mv squared over 2, I'm actually going to write 3 over 2 kT. Oh, and I keep on getting things on my computer. Sorry about that. Okay. So let's see. So I've got pressure is N over V. And I'm going to write 3 over 2 kT, where K is Boltzmann's constant. It's not super important for us right now. T is temperature in Kelvin. Whenever you see an uppercase T, assume, unless stated otherwise, it means temperature in Kelvin. And then I've got this factor of 1 over 3, and then this factor of 2 here. Okay, so all I've done, I've swapped out the mv squared over 2 in the red parentheses, set it equal to 3 over 2 kT, and I've just replaced it here. And now you can see why we did that. The 2 in the denominator and numerator cancel, the 3 in the denominator and numerator cancel, and I'm left with P is N over V kT, or I can rephrase this slightly. I can write P, if I multiply both sides by volume, PV is N kT, which is essentially the ideal gas equation, but we can make it more chemo-friendly by replacing Boltzmann's constant with the ideal gas constant. So for 1 mole of gas, N becomes Avogadro's number, Na, and we can say the term for moles, little n, is 1. So for 1 mole of gas, the number of molecules I have becomes Na, and also Boltzmann's constant becomes the ideal gas constant. So what Boltzmann does for one object, the ideal gas constant does for a mole of those objects. So we essentially know that Avogadro's number times by K equals mole times by R. So replacing NaK with Nr, we have PV is nRT, which is the typical way a chemist would write down the ideal gas equation. Shortly, I'm going to erase this board. We're going to go back and we're going to use this equivalence between the two types of classical kinetic energy, or the two ways to commonly represent kinetic energy, to come up with the root mean square velocity of gases. So earlier in this video, we'd set these two forms of kinetic energy equal to each other so that we could produce some soft derivation of the ideal gas equation, or the ideal equation of state. Now we're going to essentially manipulate this equation, solve for V, and when we do that will be the common way to calculate the velocity of gases. It's known as the root mean square velocity of gases. Okay, well firstly we notice that we have a denominator 2, which is redundant because it's equal on both sides, so we can get rid of it. So we know that mv squared is equal to 3 kT. mass velocity squared is equal to 3 Boltzmann's constant Kelvin temperature. I can solve for v squared. So v squared is 3 kT over m. And now I've got v is 3 kT over m square rooted, so raised to the half power. That essentially is the root mean square velocity. Whenever you use Boltzmann's constant, you're talking about one object. So we'd have the mass of that one object. In chemistry, it's much more useful, much more common for chemists to talk about a mole rather than an individual object. So for 1 mole, we know that K is going to become R, and mass is going to become, I'm going to put uppercase M, where this is the molar mass. So this is, if it were an atom, for example, a helium atom, this would be the atomic mass. But we've scaled by a mole, so this is now molar mass. So we've got the way a chemist would typically write this. V is 3 RT over big M, where M is the molar mass. The whole thing is square rooted. And I'm going to call this RMS, where RMS is root mean squared. So this is the common way, the average way that this is the common way to calculate the average speed of a gas. The only thing to be mindful of here is that R is going to be the unit that has joules in, so it's going to be the 8.315 joule per mole per Kelvin value. So you can get in trouble if you use the wrong value of R. So we want one with velocity units in, so that tells you to use the 8.315 value. M, we have to have in units of kilograms. Now, typically a chemist would use units of gram, but that's not going to help us because we have to cancel out the units of kilogram hidden within the joule unit. So recall that a joule is a kilogram meter squared per second squared. So if you've got joule in your numerator, you've really got kilograms in your numerator, so you have to have mass in kilograms in your denominator. And for the students enrolled in my classes, I've got many examples of this as homework questions. Okay, just to plug some numbers in and give you a feel for the order of magnitude of the size, let's calculate the root mean square velocity of an oxygen molecule at 25 degrees Celsius. Okay, so we know that VRMS is 3 RT over the formula weight, and the whole thing is square rooted. So let's just plug the numbers in. So it's the number 3 multiplied by 8.315. Now remember, we said that joule is kilogram meter squared per second squared. So rather than write joule, I'm going to write kilogram meter squared per second squared. And then I'm going to write what's left, mole. Actually, if I write it consistently, that would be best. So I'll just put mole down by the second squared because it's a denominator. So mole and Kelvin. So joule per mole per Kelvin. Now I've got temperature. Temperature has to be in Kelvin, so I'd add 273. Really, it should be 273.15, but I'm not going to split hairs over the 0.15 in this video. So that's just 298. There's a time and a place for being hair splitting. I don't think now is the time. Okay. And then we divide that by the formula mass in units of kilogram. So I know oxygen is 16 gram. I've got 2 oxygens, so that's 32 grams even. So I'm going to step over here. 32 gram of oxygen. But I don't want gram, I want kilogram. I know 1,000 gram is a kilogram, but I want my 1,000 gram as a denominator. So a kilogram of oxygen is equal to 1,000 gram of oxygen. So I've got my kilogram down here, which will cancel that kilogram. I mustn't forget to square root the whole thing. If you did forget to do that, you'd see that you'd have square units rather than the actual units you need. What else cancels? My Kelvin cancels. My mole should cancel. Where's my mole? Oh, well, this is the molar mass, so this is a weight equal to mole. So I've got kilogram is equal to 1 mole of oxygen. I didn't write it in. So 32 grams of oxygen is equal to 1 mole of oxygen. So there's my mole that will cancel mole here. And the only units that survive are meters squared per second squared, square rooted, which just becomes meters per second. So I actually don't have this calculated ahead of time. I know roughly what it is, but I'll see what it actually is. So 8.315 by 3 by 298. So I've got 7433 divided by 1,000. Okay, and then I just have to square root. So it's approximately 500 meter per second, if I just give one sig fig. So approximately 500 meter per second. And I think I pointed out the features to avoid. Make sure you have kilogram, make sure you have the right value of R. We'll pause the video. The final topic I think we should look at is Graham's Law of Effusion, and we'll look at that when I've cleaned this board. Okay, so this topic is going to be Graham's Law of Effusion, or Graham's Law of Effusion, depending on how you were raised to pronounce that word. Okay, so first of all, what's effusion? Effusion is diffusion through an aperture. Aperture is a fancy word for hole. So for example, a gas within a room can diffuse, move with kinetic molecular motion, elastic collisions, random haphazard straight line motion, incessant motion so long as temperature is above absolute zero. That's diffusion. If you open the door, the gas can effuse through the door because the door now is an aperture. So effusion is diffusion through an aperture is just a hole. So we have to make a statement first. At a given temperature, at any given temperature, the average kinetic energy of all ideal gases are the same. So at a given temperature, the kinetic energy of all ideal gases are the same. So an example, remember we said the kinetic energy was mass velocity squared over 2. Let's consider we just want monatomic gases just to simplify it. Let's consider helium and xenon. So let's consider helium versus xenon. So we know that the mass of helium and the square velocity of helium divided by the number 2, so the kinetic energy of helium, if I take the average where the line overhead just means average, is equal to the mass of xenon, the average square velocity of xenon over the number 2 at a given temperature. I've got a common factor of 2, so I can just get rid of the common factor of 2. Divide them both by 2, you may as well not divide any of them by 2. And now I can just pool like terms, and it's always a good idea, although it's not essential, that you have the mass that's lightest have that velocity as a numerator. So let's pool like terms. So I've got the average velocity square of helium divided by the average square velocity of xenon. So I basically took this down here. Let's take the mass the other side. So I've got the mass of xenon as a numerator and the mass of helium as a denominator. Now I want to square root both sides. So I can just get rid of my square here if I square root both sides. So on average, the ratio of these velocities is equal to the square root of the ratio of the masses. And notice there's a cross relationship. So if you're talking about the velocity of helium as a numerator, you have the mass of helium as a denominator. Basically says that heavy atoms move slowly and or relatively slower than light molecules or atoms which have a much higher velocity. So there's an inverse proportionality between velocity and molar mass. So in general, so this essentially is Graham's law of effusion. In general, if we have mass 1 and mass 2, then the ratio of the velocities 1 over 2 is equal to the inverse ratio mass 2 over 1 all square rooted. So this is Graham's Law of Effusion. You can also ask, notice first of all that it's a unitless quantity. So this will give you a ratio. So for example, how much faster can helium effuse rather than xenon? And we'll plug some numbers in and we'll get a feel for the outcome in a second. Before we do though, I want to mention, what if you wanted a ratio of time of effusion rather than velocity of effusion ratio? What if you wanted a ratio of time of effusion? Well, recall we said earlier when we were looking at ideal gas derivation that length is velocity by time. This is an equation we said earlier. So I can see that velocity is length over time, which means that velocity is proportional to 1 over time. So there's an inverse relationship between velocity and time, which, as you might expect, is going to flip the labels on my equation here. So this is the generic form of Graham's law for velocity. You could also have it represented in terms of time, but now you'd have to flip the labels. So you could have time 1 over time 2 is equal to mass 1 over mass 2 square rooted. And again, notice here this diagonal relationship with velocity and mass. Notice here we don't have a diagonal relationship. The diagonal is being undiagonalized because of this inverse relationship over here. And this can often catch people out, but not if you've watched this video. So in the previous slide, we had Graham's law of effusion. We used helium and xenon as examples, and we saw this cross relationship between the velocity and the mass. So let's plug some numbers in and see what a typical value would look like. So all we need to do is we need to know the mass of xenon and helium. So I've got a periodic table in front of me. So I know that the mass of xenon is 131 gram per mole. And the mass of helium, the atomic mass, is 4.0. And I need to take the square root of that, and the units will cancel. So I'm going to get a unitless number. Obviously, if this were a molecule like CO2, you would just take the molar mass rather than the atomic mass. So I'm going to enter this on my calculator really quickly. Let's take the square root. Okay, so this is 5.73. No units, no attention to significant figures. So it's almost 6. So what does this mean? This means that helium will effuse almost 6 times as fast as will xenon. So if you're on a spaceship and there's a breach of the hull and the gas inside your spaceship starts to effuse out of the hole into space, if you've got an equal mixture of helium and xenon, this is telling you that for every xenon that escapes, almost 6 helium are going to escape. So eventually your concentration that's left in the spaceship is going to change, right? Because they're leaving at different rates, so it's going to change the concentration of the mixture that remains behind. So you can get ratios of velocities from Graham's law of effusion. You can get absolute velocities from the root mean square velocity calculation that we saw earlier in the video.